All right, let's do one quick example about our temperature units. So let's say we have an object at 10 degrees C and it is heated to 40 degrees C. You know, maybe we put it on a stove or something like that. What is its temperature change in Kelvin? So this is going to come up with an equation we're going to learn in a little bit, so I wanted to address this first. Okay, so how do we do this? Well, one reliable way to do it is going to be convert both of these numbers into Kelvin and then find the difference. So 10 degrees C is equal to 10 plus 273 is 283 Kelvin. 40 degrees C is 273 plus 40, 313 Kelvin. And the difference between these two, 283 and 313, is 313 minus 283, which is equal to 30 Kelvin. Of course, this is exactly the same number we get when we subtract 40 from 10. So this is our takeaway from this. Changes in temperature in degrees C are the same as changes in temperature in Kelvin. We do not have to do any unit conversion. It is totally incorrect to do something like find delta T in degrees C and then say, oh, well, if I want this in Kelvin, I need to add 273 to it. So delta T is 303 Kelvin. No. They're the same. And yeah, just wanted to clarify that. Okay. So the first place we're going to use this idea of temperature is with a phenomenon called thermal expansion. So we have our kind of model of a solid where we have these atoms, connected together by little bonds, right? Maybe little masses and little springs or whatever. So all of these are, if we're just thinking about one row here, these could be part of a bigger lattice of these atoms. So if this is at some temperature, these atoms are all, jiggling back and forth. They have some random velocities, right? They are moving back and forth randomly. Now, if we add thermal energy to this and increase its temperature, they're going to be jiggling back and forth more, right? There's going to be a higher velocity. Now, I can't justify this next part with what we know, but you'll have to believe me that when this happens, they tend to push each other apart. Or in other words, at higher temperatures, as these are moving more, these bonds tend to get a little longer. So our picture, if we add energy or increase the temperature, our picture looks, this is exaggerated of course, but our picture looks like this, right? These spread out a little bit to make our system a little bit bigger. So this is called thermal expansion. In general, most everything that you heat up is going to expand. There are some exceptions to this, but this is by and large the rule. And how much it expands depends on a few things. It depends on how big your object is to begin with. So bigger things are going to increase their size by bigger amounts. It also depends on how much the temperature of the object changes. If you only change it by a fraction of a degree, it's not going to change its size very much because you haven't added very much energy. If you change its temperature by 100 degrees, you're having to add a lot more energy and you're going to change its size because of that. So it depends on delta T. It also depends on what the thing is made of. So we'll say the material. So different materials are going to expand different amounts because of what they're made of, because of some properties of these bonds between the atoms, the details of which we're not going to worry about. But we can write down an equation for this thermal expansion. So the equation is this. Delta L equals alpha L delta T. Okay, so delta L is the change, so L here is meant to represent length. Delta L is the change in size of our object. Li is the initial size, the initial length of our object, how much it started at. Delta T, of course, is the change in temperature. I'm not going to label that. And alpha, so this is a Greek lowercase letter alpha. This is a new variable. This is our thermal expansion coefficient. And the thermal expansion coefficient is what is including these material properties. So different materials are going to have different thermal expansion coefficients. These are things you can look up in a table or online, or in a homework problem you would probably be given the thermal expansion coefficient of a particular substance if you needed it. So a quick check on units here. Our expansion coefficient multiplied by length multiplied by temperature should give us units of length. So alpha is going to have units of 1 over degrees C or 1 over Kelvin. And because this is a delta T, these are the same units. So delta T here can be in degrees C or Kelvin. Because it is a delta T, these are actually the same. You will get the same number there. Okay. So, expansion coefficients, in general, are small numbers. And that's because if we change the temperature of something by a few degrees C, we are not changing its length by a big fraction. So, let's look at some actual values of alpha. So this is in units of 1 over degrees C or 1 over Kelvin, either way. So here are just a few materials. So aluminum has an expansion coefficient of 2.3 times 10 to the minus 5. So, well, we'll do the other one and then we'll talk about what it means. Glass has an expansion coefficient that is a few times smaller. It is 8 times 10 to the minus 6. And iron is in between the two. It has an expansion coefficient of 1.2 times 10 to the minus 5. So these are kind of, typical values for metals. You can have larger values for certain kinds of plastic. You can also talk about thermal expansion coefficients for liquids, and you can get some bigger numbers for liquids. You can also have specially engineered materials, in particular alloys, that have expansion coefficients tuned to special values. I think the most important one is something called Invar. And Invar is a alloy related to steel, I think, whose expansion coefficient is engineered to be very low. So over large changes in temperature, things made of Invar tend to not change their size very much, compared to if they were made of iron or aluminum or something like that. Okay, so putting these numbers in context, remember our equation was alpha L delta T. So this is delta L is equal to that. So what these values are how much fraction of the original length we get per degree. So in other words, if we have 1 degree change, so delta T is 1, then these values of alpha mean that the change in length we get is this fraction of the original length. So for 1 degree, an object made of aluminum is going to change its length by 2.3 times 10 to the minus 5, which is not very much. That's, 0.002% or something like that. Okay, let's do a quick example. I think that will help illustrate how we use this. So let's say we have a 30 centimeter aluminum ruler. And we heat it from 10 degrees C, maybe it's, a little chilly outside, we have our ruler, to 100 degrees C. We put it in a thing of boiling water because we want to measure how big the inside of the pot is or something like that. So what is its new length? Okay, so to figure this out, delta L equals alpha L delta T. So for aluminum, alpha, we know, is 2.3 times 10 to the minus 5. Our initial length here is 30 centimeters, which is 0.3 meters. And delta T is 100 minus 10, that is 90 degrees C, or 90 Kelvin we've increased our temperature by. So if I multiply those together, I get 6.2 times 10 to the minus 4, and these are all in SI units, so this has units of meters. So we have changed the length of our 30 centimeter ruler by 6 times 10 to the minus 4 meters. So that means in terms of centimeters, if we want to compare it to this value, that is 0.06 centimeters. So we go from 30 centimeters to 30.06 centimeters. So this is a pretty small change. This is not something we're likely to notice with our eyes looking at an object. But this is enough to make a difference. I mean, so if we're measuring something around that size and we want to measure it to the nearest millimeter, this is more than half a millimeter. So this would, change our amount we've measured by roughly a millimeter. There are other far more important examples where thermal expansion matters. The biggest ones I should mention are in things like bridges and buildings. If you have long pieces of metal or concrete that undergo temperature changes, they are going to change their size. And if L is really big, delta L can still be significant, many, many inches. And there are engineering ways of overcoming that. One is expansion joints. So if you drive over bridges or freeway overpasses, sometimes you see between two pieces of concrete, there'll be something that looks like this with like teeth overlapping. And this is an expansion joint meant to allow these pieces of concrete to expand and contract, change their length, and still have a solid roadway to drive over. There's some other fun examples of thermal expansion that I'll post some links to on Canvas as well. All right. Lastly, we can also have thermal expansion of volumes. So we were talking about, what we just saw was examples of thermal expansion in one dimension. We can also have expansion of areas and volumes. I'll just show you how volumes work. So volumetric thermal expansion, the equation is delta volume is equal to, so there's still a initial value, there's still a delta T, there's actually even still an alpha, there's just also an additional factor of 3 in front. And this is because volume is a three-dimensional measurement, and length is a one-dimensional measurement, so it has a 1 there. You can show where that comes from with calculus. We're not going to worry about why there's a 3 there. But for volume, we do need this additional factor of 3. So you can figure out things like, if you have a tank of water and you know the expanding coefficient of water and you heat that water up to some new temperature, how much does its volume change by? So, using this equation is the same as using the other equation. We're just using volumes instead of our lengths.